The half adder is a circuit in electronics used to perform the addition of two 1-bit inputs and represented as a 2-bit output. This circuit is consisted of an AND and an XOR gate. The AND gate represents the most significant bit, or the carry bit, which is this LED here, and the XOR gate represents the least significant bit, or the sum bit, which is represented here. As seen in the truth table, the AND gate, which is the carry bit, is only high in one instance, when both inputs A and B are on. Type shit. This is because each bit represents 1 and the carry bit represents 2. In this circuit, it takes the sum of the inputs, so 1 plus 1 should equal 2. This can be seen in the prototype here. When both inputs are pressed, the most significant bit is on. The XOR gate, which represents the sum bit, or this least significant bit, is only on in 2 instances, as seen in the truth table. When only B is high and A is low, then this is on, and when only A is high and B is low, it is also on. This can be represented in the prototype as well. When only A is pressed, the least significant bit is on, and when only B is pressed, the least significant bit is also on. But when both are pressed, it is not on. Similar to the half adder, the full adder adds 1-bit inputs. However, the full adder has 3 inputs, input A, B, and C. However, it is still represented in a 2-bit output. The full adder is comprised of 3 logic chips, an AND, an XOR, and an OR gate. Since the sum bit represents 1, we would expect it to be on only when there's an odd number of inputs pressed. Therefore, it is only on when there's either 1 input pressed or when all 3 inputs are pressed. This can be seen in the breadboard prototype. Referring to the circuit diagram, we can see that the sum bit is high only when there's an odd number of inputs pressed, because when only A is pressed, for example, this is low and this is high, making this XOR gate high, making the sum bit high. When all 3 are pressed, this is low and A is high, making this high and making the sum bit high. However, when 2 inputs are pressed, for example B and C, this is low and this is also low, therefore this is also low. The carry bit is only on when either B and C are pressed, or when A and B or C is pressed. This will make this OR gate high, making the carry bit high. This can be seen in the truth table. Finally, the 2-bit adder. The 2-bit adder has 2 2-bit inputs and a 3-bit output. Since it has 2 2-bit inputs, which each can be 3, the maximum output is 6. The scenario where 6 is produced in the output can be seen in the last row of the truth table. A1, A0, B1, and B0 all are on, making the carry bit and sum 1 output on. This can be seen in the breadboard prototype. The 2-bit adder is comprised of 3 logic chips. However, more gates in these chips are used, as seen in the circuit diagram. It is comprised of an AND, an XOR, and an OR gate, like the full adder. The most significant bit, or the carry bit, is on when the sum is greater than or equal to 4, because the most significant bit has a value of 4. The second bit, or sum 1, is on when the sum is 2, 3, or 6. The reason it's not on when the sum is 4 is because the most significant bit is 4. Therefore, it should not be on. The least significant bit, or the sum bit, is on when the sum is odd, because the least significant bit has a value of 1. Therefore, when it's on, the value is odd. And here's the final 2-bit adder on the PCB. As you can see, this is input A1, A0, B1, B0. In conclusion, the 2-bit adder is the most advanced adder out of the 3, which can add 2 2-bit inputs, which produce a 3-bit output.